Now that you know how to draw the structures, we can go to learning how to name the structures. There's 4 parts to any organic chemistry alkane name. The first is the prefix. That tells you where and what is in the group. So if you have alcohol groups, that's going to give you the address of where things are. The parent tells you how many carbons are in the longest carbon chain. The locant is where the primary functional group is, and the suffix tells us if there's a functional group or not. So the first rule is to find the parent hydrocarbon chain, which is the longest continuous carbon chain, and then we use that parent as a name. In this example here, the longest carbon chain is highlighted in pink. It has 1, 2, 3, 4, 5, 6. For a compound with a 6-carbon longest chain, it's going to be named hexane. This one here, the longest carbon chain, is 1, 2, 3, 4, 5, 6. This one will also be a hexane. This longest carbon chain here, but we want to maximize the number of functional groups. This would be a hexane with 2 substituents, while this one is a hexane with 1 substituent. Intuitively, it would seem like this would make more sense to streamline or make it simpler, but this is the preferred version. The second rule, carbons that are in the main chain are numbered in sequence to give the lowest numbering possible. In the first example here, the substituents that are coming off carbons 3 and 4, while in this group, the substituents are coming off of 4 and 5. So you want to give it the one that has the lowest numbering. Number 3, substituents are identified and numbered. So once you've numbered the long chain in an order that gives it the lowest numberings, then we number and name where each of the groups are. This first one here, this is a CH2CH3 on the 3rd carbon, so this would be 3-ethyl. This is a 4-methyl, because there is 1 carbon. This also has 1 carbon. This would be 7-methyl. So 7-methyl, 4-methyl, 3-ethyl. And the parent here has 9 carbons. That would be nonane is the parent here. This one, the parent has 6 carbons. This is hexane. And the group here on CH3 on number 2, this would be a 2-methyl. This is 1 carbon, so this would be 4-methyl. And this is 4-ethyl. For the last step, you put all of the things together. We're going to name the substituents and identify them, and then list alphabetically. So for this one, we have 3-ethyl, 4-methyl, methyl. Ethyl comes before methyl. This would be 3-ethyl. We have 2 methyl groups, so what you would do is put a hyphen here. We're going to give the 2 numbers, so 4 and then 7. Because there's 2 methyl groups, we use di to illustrate that there are 2. So it'd be dimethyl, and then the parent name is nonane. That is how we would name that one. This one over here, we have ethyl, methyl, methyl. This would be 4-ethyl, 2,4-dimethyl, and then hexane. Again, we use di to indicate that there are 2 methyl groups. The 2 and the 4 tell us where those groups are. All right, so we're going to look at a couple of examples here. The first one is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 either way. 5 carbons is pentane. We have no other groups coming off of there, so that's how we would name that one. In this example here, the longest carbon chain has 1, 2, 3, 4. There's 1 group coming off of here, and that is a methyl. It's a 2-methyl. I numbered it this way because if I numbered it the other way, it would be 1, 2, 3, 4. So this would be 2-methyl butane. This one, the longest chain is here. I'm going to number 1, 2, 3, 4, 5. If I numbered it the other way, it would be the same thing. I have a 3-methyl and another 3-methyl. In this case, I have both methyl groups on the same carbon, So I need to list where both of those are. 3, 3, 2 methyl groups becomes dimethyl. 5 carbons is pentane. In this example, we have the longest carbon chain, 1, 2, 3, 4, 5, 6, 7. If you numbered it the other way, the branch would be coming off of carbon 3. Here it comes off of 2. I have a 2-methyl. This is 2-methyl. This is 5-methyl. So we have 3 methyl groups, and you're going to list where each of them are. So it becomes 2, 2, 5. There's 3 of them, so that is trimethyl. 7 carbons is heptane. So if we look at this one here, the longest carbon chain is 1, 2, 3, 4, 5. There's 2 groups here. This is a 2-methyl, that's a 4-methyl. So we have 2, 4 dimethyl. 5 carbons is pentane. This one here, if we look at the longest carbon chain, 1, 2. This is an ethyl group at 4. So we have 4 ethyl. 9 carbons is nonane. To go from the name to the structure, we're just going to draw what the name says. You can start backwards. When I'm drawing the structures from the name, I like to start with the parent. So nonane is 9 carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Methyl, there's 2 of them, which is 2 CH3 groups on carbons 3 and 4. 1 here and 1 there. If you had drawn the carbons on 3 and 4 coming that direction, that would be the same thing. So here I'm going to start with octane. 8 carbons. At 4, there is a propyl, which is a 3-carbon linear chain. So 1, 2, 3, and then 2, 2 dimethyl. Heptane. I have dimethyl at 4, and 1, 2, 3 ethyl. For pentane, here's 5 carbons. Trimethyl means there's 3 methyl groups at 2, 2, 4. Alkanes are sometimes referred to as paraffins because they're low affinity compounds, and they generally don't react with very many chemicals. They will burn in a flame producing carbon dioxide, water, and heat, also known as a combustion reaction. The alkanes are present in natural gases, including methane, ethane, propane, and butane. Propane you may have seen in LP gas. Some of your homes may be heated by propane or use it for gas grills, and butane is in little lighters. Petroleum is often a mix of different alkanes found in crude oil form, can be separated by their different boiling points. So you can see in the figure here, there's crude oil that is being heated up, and as the temperature increases, the more volatile gases are the ones that will travel higher and have the lower boiling points, and those will get collected up here at the boiling point range below 20 degrees. Gasoline has boiling points between 20 and 200. Kerosene is higher. Fuel oil and then lubricating oil has temperature above 400 degrees. Any residue that's left over is converted to asphalt. Alkanes can react with chlorine in the presence of light to replace hydrogens with chlorines. This is a very uncontrolled reaction. If you have methane, which is CH4, with chlorine in the presence of light, such as the sun, one of the hydrogens, CH4, is replaced with the chlorine. That reaction can happen again to give CH2Cl2. That reaction happens again, etc., to end up with CCl4 plus HCl. This makes chlorofluorocarbons very dangerous. If you have a chlorofluorocarbon, which used to be present in refrigerants a long time ago, these compounds can form radicals, which is an unpaired electron, in the presence of light from the sun, and form these chlorine radicals. So here's a couple of different examples of chlorofluorocarbons that are present. Freon is one of them. These are the alternatives that have been given to replace the chlorofluorocarbons, so they're not producing the chlorine active radicals. So when CFCs are present, They deplete the ozone, which puts a hole into the ozone layer, and that causes the sun's harmful UV rays to enter into the earth. So these chlorofluorocarbons are emitted from things like old refrigerators that eat up the holes in the ozone. So there's sources of stratospheric chlorine include only 15% are from natural causes, 3% is from hydrogen chloride. All the other CFCs or the stratospheric chlorine is from things that we have put out there. So the CFC molecule, when it encounters UV light, causes the chlorine to break away. The chlorine radical that we saw form earlier can interact with the ozone. That removes an oxygen from ozone, creating oxygen molecule. Then there's a free oxygen molecule available, and then that can pair up with another ClO and releasing the free chlorine to attack things further. If we look at the ozone destruction over time, in 1979, this was the shot of the ozone layer here, which seemed to be covering the Earth, and in the next decade, the hole grew bigger, and you can see in 2010 how big the hole in the ozone is now. We're going to change gears a little bit here. So ethane can take different conformations, which involves discussing the topic of stereochemistry. Stereochemistry refers to the 3D aspects of molecule in space. Sigma bonds are cylindrically symmetrical. That means we can rotate around the carbon-carbon bonds. If we look at this drawings down here, this is the ball and stick figure where the hydrogen is down, these two out to the side. We can rotate that around so that this hydrogen is now sticking up. So if we were to duplicate the same picture, the hydrogen would be up here and then these two would be down. A conformation is a different arrangement of the atoms that results from rotating the bond. So this is the structure of ethane. The two black balls here represent carbon, and this is the bond in between there. So if I'm looking at this ethane here, I can change the conformation by rotating it around the bond. That's what it's referring to when it's talking about different conformations. So this can also rotate around the carbon-carbon bond. The structure hasn't changed. We haven't moved any bonds. We're just rotating those bonds. When we draw conformations, it can be represented in two ways. The first one is the sawhorse conformation, which we've already seen. So in the back here, you have the hydrogens. And in the front, there's this hydrogen here. So you can see this is the same type of drawing here. The other type is a Newman projection, which is the bane of several organic chemistry students' existence. So what this is showing the front carbon only. And I'll show you this in the model momentarily here. And you're showing the hydrogen that's coming out of the top, one that's coming here, and this one here. So this is the front carbon. You can see the hydrogens coming out from the back carbon. This circle represents the back carbon. And on the back carbon, I have the hydrogen, hydrogen, hydrogen. So that is a Newman projection. So in the Newman projection, this is what we saw. This is the same two carbon molecule. We drew the sawhorse conformation, and then this is the Newman projection. We're just seeing the front. There's a bond that is not shown in the Newman projection. It shows the front and what's bonded to the front carbon, and then we show what's bonded and coming out of the back carbon. So that is a Newman projection. There's different conformations of the Newman projection within itself. In a staggered, all 6 of the CH bonds are as far away from each other as possible. So if I was going to draw the staggered conformation for ethane, which we just saw in the video, this would be the sawhorse, a not very pretty one. But the front carbon here had an H. These are coming out at the correct angles here. The back carbon also shows 3 H's. This is the staggered conformation. All of these H's are as far apart as possible. In the eclipsed, all CH bonds, all 6 of them, are as close as possible to each other. So for the same compound, I'm going to leave the front carbon where it is. I can rotate around the back, so now the hydrogen here is directly behind the hydrogen in front of it. So they're eclipsing each other. This is eclipsed. This one is favored. It's lower energy. It is lower in energy because all of these hydrogens have their own little window. They don't have to compete for space. So if you can think of when you're trying to take a group picture with people and the photographer tells you to find your little window so that nobody's blocking you, this is what the staggered conformation is. And I'll show you this in the atoms here. So, right, so here's the ethane again. This is the staggered conformation where all of these are far apart from each other as possible. If I rotate it just 60 degrees, now it is eclipsed. You can barely see the hydrogens that are behind these front hydrogens here. So this would be staggered, which is lower in energy and is favored. This is eclipsed. So what we want to do is draw butane, looking down the carbon 2 carbon 3 bond, label each of them as staggered or eclipsed, and then determine which is the most stable. If we're looking at butane, butane is 4 carbons. 4 carbons, we're going to look down carbon 2 and 3. So I'm going to show you first what that looks like on the models here. I'm just showing the carbon chain here. I left. Okay, so here is the structure of butane. I have 1, 2, 3, 4 carbons. We're going to view it looking down carbon 2 and 3. So this is what you can see is viewing it down 2 and 3. So what you see here from the side, this is the carbon 2 and 3. This is in the staggered conformation where the large groups, these ones here, are farthest apart from each other. So we're going to start with drawing the dot on this first carbon, the CH3 group coming off of there, and these 2 H's, and then the back carbon we have 2 hydrogens and the CH3 group there. So that is the staggered conformation. So again, the front carbon, we have the dot representing carbon 2. There was a CH3 coming out of the top. I had 2 hydrogens off to the side. In the back carbon, in the staggered, this was coming straight out of there on the bottom. H and H. So this would be the staggered conformation. So in the Newmans, you need to show all atoms bonded. There's nothing implied on Newman. So if there's a hydrogen, you can't just leave it off. It needs to be shown on there. All right, in the other one, I'm going to leave the CH3 in the same spot. I'll demonstrate with the models what the eclipse looks like. So here's our butane again. This is our eclipsed. I'm going to do a rotation here around the bond. So I'm just twisting it. And now these are eclipsed in front of the other. The hydrogens are blocking each other. These hydrogens are blocking each other, as are the CH3s. So this is the eclipse. So to go from the eclipse to staggered, it's just a bond rotation. And then you can rotate it back to get to the eclipsed. So to draw the back carbon, I have the circle. For the eclipsed, I had the CH3 here. This H, I think I had them down in the models, but the gist is the same. So these large groups are blocking each other. These small ones are blocking each other. This is eclipsed. We've labeled the 2 as staggered and eclipsed. This one is lowest in energy because nobody's blocking one another, which means it's the most stable. So there's one more conformation that is referred to as a gauche conformation, and it's a form of staggered. See if you can see the difference here. This one is called gauche. So the difference between a gauche and the staggered, in the staggered, the large groups that are on each of the carbons are opposite from each other, or anti. This is an anti-staggered. This is considered staggered as well, but it is a gauche staggered, or just regular staggered. The larger CH3 groups are not blocking each other directly as in the eclipsed, but they're not opposite from each other. So this one can still feel the personal space bubble of that one right there. So it's going to feel some interactions in between there. So this is the anti-staggered. This is just a staggered, or is referred to as gauche. And this is eclipse. This one is lower in energy than eclipse. So now we have the question of drawing Newman projection for the most stable conformation of pentane, looking down C2, C3. So I'm going to start with drawing pentane, which is 5 carbons, looking down this bond. And we're drawing the most stable, which will be the anti-staggered. So I'll start with the front carbon, which has a CH3. It's got 2 hydrogens. So we don't show the bond here. This one back here, this is C3. That is C3. And on C3, there's a CH2, CH3. And the 2 hydrogens here. So this would be the anti-staggered of pentane. We next want to draw the Newman projection for the least stable conformation of 2,3-dimethylhexane, looking down the same 2,3 bond. 1, 2, 3, 4, 5, 6, and then 2,3-dimethyl. We want the least stable, so it's going to be the eclipsed. On the front carbon, I have 2 CH3s, and this is a hydrogen. Looking at the back carbon, there's a CH3 directly behind. Then I have a CH2, CH2, CH3, and a hydrogen. So this is the eclipsed.